Welcome back, everyone. In today's lecture, we're going to talk about torque, which is basically the rotational equivalent of forces. So we're talking about essentially Newton's laws here, um, as they apply to rotation. And in particular, a torque, we will find, is the action of a force that causes an object to change its state of rotation. Right? So to cause the pen here to turn, I have to exert a force that will cause a torque. And that means that I have to push on certain parts of the pen. If I push on the ends of the pen, I can cause a thing to turn. But if I try and push through close to the center of the mass of the pen, it doesn't rotate very well. And so the location on our object where we apply a force will turn out to be important when calculating the torque on that object. Let me suggest, before we move on here, that you pause the video for just a moment and go find yourself one of the heavier doors available to you, maybe the front door of your of wherever you're staying, and try an experiment. Try to open or close that front door by pushing on the side farthest from the hinges, and then try and do the same thing by pushing on the side right next to the hinges. And just observe how easy it is to close the door or open the door from the two sides. Earlier today, I did this experiment in my own living room, and we can look at the results here. So here, pushing on the side far away from the hinges, I can use my pinky finger and even a bent pinky finger. It takes almost no force to push this door shut. But if I try and do the same on the other side, nothing happening, and indeed I have to apply several fingers and a fair bit of force here to get the door to push closed. So what does this imply in the context of causing a torque, causing a turning or an angular acceleration, essentially, of a body? So if our object is rotating around an axis point, right? So here, for instance, down here at the bottom, that would be the hinge of our door. Then what we'll find is the farther away from the hinge that you're pushing on the door, the more easily that door will accelerate and the more easily that you can cause that object to rotate. So distance from whatever the anchor point of the rotation, whatever hinge or whatever it is that is the defining the point around which our object is rotating. All right, so here it's right about here where the center of mass of our pen is. The farther you are out from that, the easier it is to cause a torque. Whereas if you're pushing it right next to that anchor point, that axis point, it's harder. So we would expect that our torque here must be proportional to the distance from our rotation axis. Another thought experiment, you could try this again with your door. If you try and pull or push along along the line that connects our rotation point to our rotational axis to the place where we're applying force, if we push along the side, if you try and pull a door sort of along parallel to its surface, it doesn't accomplish very much. Indeed, it's only forces that are applied sort of perpendicular to that position vector r here, where r here is the position vector that represents the vector that takes you from your axis to the place you're applying the force. This position vector, this force vector, it's only the components of that force vector which are perpendicular to this position vector which cause twisting motions. A parallel component of force, one that would be directed along this this radial position, or this radial position vector, those aren't generating twisting motions. Those are just trying to stretch or shrink your object, and it will be battling with the internal forces in the pen, or whatever it is in the door, whatever it is that your solid object is doing. So it's only perpendicular components of force that, excuse me, it's only the perpendicular components of force that contribute to the twisting motion, to the turning motion, to the torque. And so, obviously, the harder you push, the stronger that twisting motion is. And so we're left here with this idea that it's the strength of the perpendicular component of force multiplied by the distance from the axis that gets you, or that tells us how much twisting motion will be applied, or twisting force will be applied to our object. And so the definition of torque here is, again, this distance from the axis to the place where a force is applied times the strength of that force times the sign here of the angle between the radial position vector and the force vector. So it's this theta here, this phi here, which is the angle between the direction of our radius vector and the direction of our force. This could also be interpreted, f sine theta, as the length of this vector, which is the perpendicular component of our force vector. So we could also interpret this as saying that the torque is the position, or the distance r times the perpendicular component of force. We could even interpret it as the perpendicular component of the radius vector, so the perpendicular component of our position vector, perpendicular relative to the force vector. And so it would be the force times this length here, which we call the moment arm. And this this line along which the force is applied is referred to as the line of action, and the r perpendicular here is the distance from the axis to the moment arm. All of these are mathematically equivalent to this statement, r times f times the sine of the angle between them, but they have different interpretations, and in different contexts they can also all be useful for calculating torque. The most general way mathematically to express this concept of torque is as a vector cross product, that torque is the vector cross product of the position vector crossed with the force vector. Now, to explain that, we have to talk a little bit about what a position, or what a vector cross product is. So for those of you who haven't seen this before, or for those of you for whom this has been it's been a while since you have seen this, we ran into already when we talked about work, we ran into the hang on a sec. So when we talked about the work, when we talked about work, we ran into the concept of a dot product, which was a way of multiplying two vectors together and getting a scalar quantity out of it. In the case of work, it was the force vector dotted into a displacement vector, so F dot D, or F dotted into a displacement vector. And that was a way of taking the magnitude of the force and the magnitude of the displacement and multiplying them together with a cosine term in there to give the sort of the magnitude of that scalar quantity. But there, you can also multiply two vectors together in such a way to get a third vector, and that's called the vector cross product. And the magnitude of a vector cross product is indeed the magnitude of vector A times the magnitude of vector B times the sine of the angle between them. But being a vector product, it is a vector. It has a direction of its own, and in particular, the direction of the cross product vector will always be perpendicular to both of the two vectors it's generated from. So if you have, for instance, vector A and vector B, there's a plane defined by the plane which contains both A and B. So if the green and white pen is my vector A, and the black pen here is my vector B, and I want to talk about A crossed into B, then the resultant vector will be perpendicular to both of them. It will be, since the plane here would be the plane of the page, the cross product would be perpendicular to that and have a direction which is given by the right-hand rule, another version of the right-hand rule that we introduced in the previous lecture. So there's a couple of different ways that you can do a right-hand rule for a cross product. So one of the ways is that you say you take your right hand and you place your thumb in the direction of vector A. So again, if this is A and that's B, so we would take our right hand, place our thumb in the direction of A, place our pointer finger, our finger gun here, in the direction of vector B, and then our middle finger would be perpendicular to both of them and pointing, well, you can't really see it. In this case, my finger is pointing straight down. So you make a sort of a shape like this, and so A crossed into B would give us this downward direction. If it was, let's make it B, A now this way, so A crossed into B would give us a vector pointing upward here. Now, personally, I find this one kind of a little bit awkward, but if it works for you, that's great. Another way we could do it is you take your hand, your right hand, point it along the direction of vector A, and then you curl the fingers of your right hand towards the direction of vector B. So A crossed into B, and now your thumb points in the direction of the vector. If you're real familiar with using screwdrivers, then the direction of righty-tighty, lefty-loosey is also given by the cross product. So in this case, if you're twisting your screwdriver from A towards B, then the direction of motion of the screw would be in the A cross B direction. Personally, I find the finger wrapping method is the easiest to manipulate my hand around. It can be awkward depending on exactly what geometry it is you're trying to do to, sort of twist your right arm around to get things in the right direction. Do make sure to use your right arm. If you're right-handed, for instance, and typically write with your right hand, you will have to put the pen down to properly use the right-hand rule. I can't tell you how many times as a beginning physics student before I remembered this particular piece of advice that I tried to do the right-hand rule with my left hand. Does not work very well, I can tell you. It will 100% always give you the wrong answer if you try and do the right-hand rule with your left hand. So the direction of the cross product will give you the direction of our vector. So if we have, again, if we're twisting around this point down here, and we have a force vector in that direction, then r crossed into F, that would give us a torque vector upward. Now notice that that would produce an angular acceleration here that would be counterclockwise, and so the direction of torque also matches the direction of the angular acceleration by using the right-hand rule that we talked about last time. And so this is why that particular convention for the right-hand rule was used for determining the direction of the angular vectors that we talked about in the last class. So let me comment a couple of other things about torque. So the direction, as I've just said, will be perpendicular to the force applied. It will also be perpendicular to the line from the axis to the place at where the force is applied. That it will only be perpendicular forces that will generate torques, and that the torque itself will also depend on where you're rotating around, right? So that the torque is different if you're rotating around an axis at the end versus rotating around the middle. Even the same force applied to the same object will produce a different torque. And so to calculate torque, we have to know which axis we're rotating around. So we have to choose, or have chosen for us by the nature of the problem, the axis around which rotation will take place before we can define torque. This was not true of Newton's laws when we applied them to translation. It didn't matter where on the object we were applying the force. Newton's laws worked the same regardless of where we were applying the force. But torques are different. It matters where we apply the torque, and it matters where our object is going to rotate. Around what part of the object our solid body will rotate. Those are important factors in calculating even the value of the torque, let alone the result of that torque. All right, so let's give ourselves, let's try an example here and see if we can apply it. All right, so it says a machinist, is using a wrench to loosen a nut. The wrench is 25 centimeters long, and he exerts a 17 Newton force at the end of the handle at a 37-degree angle to the shaft of the handle. What torque does the machinist exert around the center of the nut? All right, so let's draw ourselves a picture. There's the wrench and the shaft of the wrench, and I'm going to give it a double-ended look. And it's 25 centimeters long, and the axis around which our wrench is going to turn is going to be right here. So 25 centimeters from the point around which the wrench will turn to up here, where we're applying a force. And we're exerting a force, so our position vector, our radius vector, will be this vector there. And then we're applying a force at a direction like so, 37-degree angle between the direction our force would have, or our radius vector goes, and the direction of our force. Here, this is our 17 Newton force. So the torque, the magnitude of the torque, is going to be R times F times the sine of that angle between the two of them. So that's 25 centimeters, or 0.25 meters, times 17 newtons, times the sine of 37 degrees. Okay, so 0.25 times 17 times the sine of 37 gives us the magnitude of torque of 2.56, and our units here are newtons times meters, which is interesting because we've already run into a unit of Newton meters. That was the joule. The joules, units of energy, were Newton meters. These Newton meters don't have the same meaning as the Newton meters, which are joules, because we're getting these Newton meters by a different method. Remember, joules we got from work, which was a force dotted into a distance, and that was a scalar quantity. But we could think about the concept of Newton meters in this case as being a force applied through a distance. Here, the Newton meters, the best way to think about that is a force being applied at a distance, right? So work gives you a force pushed through a distance, and that gives you energy. But a force applied at a distance doesn't give you energy, it gives you a torque. So in this case, our torque is 2.56 Newton meters, but not 2.56 joules. We can't apply joules as the units of torque here. What direction would this vector be? Right, well, our radius vector goes like so. So we go R crossed into F. So we take our hand, right hand, we point it in the direction of R, the position vector. We bend our fingers towards the direction of the force, and the thumb points up. So the direction of our torque vector would be up. We could represent that as a circle with a dot in it because we're looking down the arrowhead at us. We could use this one, R cross F, again gives us a torque going up. R cross F. Yeah, see, this one's awkward. R cross F gives us a torque going up like so. So that also would give us this same upward directed force. It has to be perpendicular to both the radius vector and the force vector. An upward directed torque is a twisting motion like so. If you grab with your right hand that upward directed arrow with your thumb pointing in the direction of the arrowhead, then your wrist would twist in the direction of force, which is what we would think. If we're applying a force sort of that way to this wrench, it's going to cause the wrench to twist like so. What would the maximum amount of torque that could be exerted with this force? Well, that would be when this sine of 37 term was 1. So the maximum torque would just be R times F. So that would be 0.25 meter, or 0.25 meters times 17 newtons. So 0.25 times 17 would give us 4.25 still Newton meters. And this is when F is perpendicular to the position vector. So in other words, we would have to have the situation that our radius vector looked like this, our position vector looked like that, and we would have to have applied that 17 Newton force like so, or equivalently also like that. But we would have to apply that force in a completely perpendicular direction so that the sine theta or sine phi term here would be sine of 90 degrees or minus 90 degrees. So this would give you a plus or minus 1, the maximum amount of torque that you can get out of any force applied at any particular distance. All right, so enough about the definition of torque. Where do we go from here? What do we do with torque? We have to relate it somehow to the changing or twisting motions of rotating objects. Well, if torque is like force, Newton gave us a picture that said, from Newton's second law, that the forces produce accelerations, and that they are impeded by inertia. Well, we could assume that the same thing will hold in the case of rotation and say that torques produce angular accelerations, but that they are impeded by however difficult it is to change the state of rotation of our system, some sort of a rotational inertia, right? So we could be looking for a relationship of this form. It looks like Newton's second law, but we've replaced all the pieces of Newton's second law with rotational analogs. So force becomes torque, linear acceleration becomes angular acceleration, and translational inertia becomes rotational inertia. Well, let's examine this idea of rotational inertia. We've already met torque and we've already met angular acceleration. Let's look at what we would need out of a rotational inertia to make that work. Well, so a rotational inertia, that's going to be the tendency of an object to resist changes to its rotational state in the same way that mass is the tendency of an object to resist changes to its translational motion. The units have to be the units of torque, which are Newton meters, divided by the units of angular acceleration, which are radians per second. So if we divide Newton meters by radians per second and expand out newtons being kilogram meters per second squared, we can cancel the second squared and the meters get multiplied together. So that would be kilogram meters squared per radian. And it turns out radians are always unitless quantities. One of their charms is because a radian is defined as the ratio of two lengths, the length of an arc versus the length of a radius. And so technically, from a mathematical point of view, radians don't have any units, so we can sort of let them appear and let them disappear as necessary in our unit analysis. And so the true units of rotational inertia would have to be a mass times the square of a distance, kilogram meters squared. Okay. That's interesting and it's suggestive. We don't know quite yet what rotational inertia would look like, but we'll get to that. Let's just assume for the moment that there is such a quantity and that you can measure it somehow. How would we use this? Well, we could use it in a problem like so. So it says the flywheel of an engine has a moment of inertia of 160 kilogram meters squared. Again, we don't know what that moment of inertia is, but we can use it. So the symbol for moment of inertia is usually an I. So we can say that the moment of inertia here is 1.6 kilogram meters squared. Sometimes sometimes you'll see this written as J, capital J. I'll use capital I. Inertia. I guess it sort of makes a certain amount of sense. So this is the resistance of our flywheel to change its rotation, right? And it says what constant torque is required to bring it up to an angular speed of 400 revolutions per minute in 8 seconds starting from rest. So our final rotational velocity, our final angular velocity here is 400 revolutions per minute, or RPMs. And it takes us a delta t of 8 seconds to get there. So if we go to the relevant kinematic equation, that's going to be our final angular velocity is our initial angular velocity plus our angular acceleration times this delta t, this time interval. And in this case, if we're starting from rest, then our initial angular velocity is 0. And so our angular speed, our final angular speed is just alpha times t. And if we want to solve for that acceleration, then, or that acceleration is also, again, if we assume that Newton's law style relationship holds, then the angular acceleration is tau, the torque divided by the inertia. So if we plug this in for our angular acceleration, torque over inertia times time, and we solve for the torque. It's asking for how much torque do we need. So our torque then is our inertia times our angular velocity divided by the time interval. So that's our inertia was 1.6 kilogram meters squared. Our velocity here is 400 RPMs, but we should convert that to a more consistent unit here. So we're going to need to convert that to MKS units. So that would be 2 pi radians per revolution. And minutes, convert those to seconds. 1 minute is 60 seconds. And divide all of that by our time interval here, which was 8 seconds. So we take 1.6 times 400 times 2 times pi. We divide by 60. And we divide by 8, and that gives us a torque here of 8.4 Newton meters. So assuming that there is a relationship like this, that's how we would use it. So now we have to show that that relationship actually works, and the way we're going to do that is by using the relationship that we know works, Newton's second law, and going from Newton's second law and deriving this based on our definition of angular acceleration and torque. So we're going to look for something of this form. And in general, if we can set up a system and calculate the torque on that system and calculate what the angular acceleration of that system would be based on applying Newton's second law in its translational form, then we can use the relationship of the torque and the angular acceleration to derive a way of calculating the moment of inertia. So we're going to choose as our rotating solid object about the simplest rotating solid object that we can. In particular, we're going to take some point mass here and glue it to a massless stick, a very light but rigid rod that will hold this composite object stiff, but all of the mass of that object will be out here, so that we can apply translational motion and Newton's second law to this object and calculate its motion. So if we apply some force to it like so, we can break that force into its perpendicular and parallel components. The perpendicular component of that force will just be counterbalanced by the tension in our stiff rod, which is holding this mass at a fixed distance from our axis. And so when we do a free body diagram, the parallel component of force and the tension just cancel one another out. And so the net force acting on our mass here is just the perpendicular component of force. That's the only one that's going to cause motion to happen. So the acceleration is just that perpendicular component of force divided by the inertia, or the mass of our object. And that's going to produce a tangential acceleration. That's going to produce an acceleration around the outside of a circle, because this mass is obviously going to move in circular motion around this axis point. So we've got a tangential acceleration, which is r times the angular acceleration. So F perpendicular, the perpendicular component of force then, is just m times r times that angular acceleration. Now our definition of torque was that torque is r times F perpendicular. So this we can turn into a torque by, well, converting F perpendicular into torque over r. And so torque over r is mRa, which means that our torque must have the magnitude of mass times the length of our rod squared times the angular acceleration. And since the torque is I times the angular acceleration, that must mean that in the case at least of our simple model of just a ball at the end of a massless rod, so a mass m out here at a distance r from the axis, the the moment of inertia, which is what it's called, or the rotational inertia, is mr squared. This does, in fact, give us kilogram meters squared as units. So it has the right units to be a rotational inertia. It has the right units to be what often gets called the moment of inertia. And we can generalize this. What if we had an object which was made of two masses connected by a network of rigid rods? That the mass was entirely in these two masses, well, then we could repeat this and so on and so forth, right? And we could even go and calculate the moment of inertia for continuous objects by taking r squared, multiplying it by a mass density, and doing a volume integral. Those of you who, if you are taking Calculus 2, will probably have seen things like this, ways to calculate volumes. This is a version of that. And so you can do that for simple shapes and
Your textbook has a number of examples. So for instance, a thin ring, all of the mass of this ring is all at the same distance, and so it's just mr squared, just like our point mass was mr squared. And it could be a flat ring, a two-dimensional flat ring, or it could be a cylinder with a relatively thin outer shell. If it's a thicker outer shell, then you've got this difference between the radii to work with. In general, here's a bunch of versions of simple shapes for which you could calculate the rotational or moment of inertia. And if this was more of a calculus course than a physics course, we would probably have you calculate all of these. In this being a physics course where we're interested mostly not in testing whether or not you can do volume integrals, but testing whether or not you're understanding the concept, then we will tend to give you these formulae for constant density objects of various types. So a cylinder or disc, where it's like a ring except we filled in the ring, that's 1/2 mr squared, as opposed to a hoop or a ring, which was just mr squared. A solid sphere gives us 2/5 mr squared, whereas a spherical shell 2/3 mr squared, and so on. Again, these particular results, you can find them in your textbook, and we would be supplying them in the context of exam questions. However, given this, now we can do some examples, some slightly less concocted examples than we did before. So here it says, for instance, you have a horizontal grindstone, a disc, that has a mass of 85 kilograms. So the mass is 85 kilograms of our disc, and a 0.35 meter radius. So a radius here of 0.35, and it's turning at an initial angular velocity of 94 RPM. You press a steel axe against the edge with a force of 18 newtons in the radial direction. All right, so here's our disc, and here's the blade of our axe, and we're applying a force like so, 18 newtons. There's our radius. So there's an 18 Newton force pushing in, and that's going to create a reaction force of 18 newtons pushing out. So there's our normal force. If we look at this point of intersection there, then again there is this normal force of 18 newtons pointed outward. And if our wheel is turning counterclockwise, so in the positive direction, then there must be a friction force in the negative direction because it's trying to counteract that moment. And the magnitude of that friction force is going to be our coefficient of friction times the normal force. So in this case, our friction force is 0.2, the coefficient of kinetic friction, times 18 newtons, the magnitude of our normal force, which is also the magnitude of the applied force. So 0.2 times 18 gives us 3.6 newtons. That's the magnitude of the kinetic friction force. So now we have, acting on our wheel here, which again is rotating like that, a kinetic friction force there being applied at this point R away from our axis of rotation. And so the torque generated would be R times the friction force times the sine of 90 degrees, because there's a 90-degree angle here between those two forces. So that's going to be our 0.35 meters times our 3.6 newtons, or 1.26 newtons at a Newton meters, so newtons applied at distance. Okay, but what we want to calculate is the angular acceleration. So now we have to use the other torque equation, our rotational equivalent of Newton's second law. And to do that, we need to know the inertia, the rotational inertia of our flywheel. So if it's a disk, then our rotational inertia is 1/2 mass times r squared. So in this case, that would be 1/2 times 85 kilograms times 0.35 meters squared. So 0.35 squared times 85 divided by 2. So our rotational inertia is 5.2 kilogram meters squared. So we know the torque, we know the inertia. That allows us to calculate our angular acceleration. In this case, our radius vector is to the right, as I've drawn it on here. So we've got, let's do this one. So our radius vector is to the right. Our force vector is down. All right, so to do that, I'd have to twist my arm around like so, to the right and down, and my finger is going to point down. We could also do this R crossed into F. So R crossed into F, again, gives us thumb pointing down. So the direction of this torque is into the page, which would be a twisting motion like that, or a negative direction with a magnitude here of torque over inertia. Basically here our torque would be negative, so that's going to be our minus 1.26 here. So minus 1.26 Newton meters divided by 5.2 kilogram meters squared. It's going to give us our minus 0.242 radians per second squared. All right, so we're slowing down at 0.242 radians per second squared. How many turns would it take to come to rest? Well, we can go and use this final velocity squared minus, or equals initial velocity squared plus 2 alpha delta theta. So the old kinematic equation. In this case, our final velocity is 0. It comes to a stop. And so our initial velocity squared equals minus 2 alpha delta theta, or our angular displacement is omega naught squared over minus 2 alpha. And in our case, that's going to be 94 rotations per minute squared over minus 0.242 radians per second squared. All right, well, there's a mismatch there. So let's give ourselves a little bit more room to deal with the mismatched units. So again, our delta theta here is 94 revolutions per minute squared divided by minus 0.242 radians per second squared. And if we want to take that radians per second, well, let's see, let's go up here. 1 revolution is 2 pi radians, right? So we're going to want to cancel that revolution, so we need to turn that around, don't we? We need to have the revolutions on the bottom. So 2 pi radians over 1 revolution, and square that to get rid of that squared. And let's turn those minutes into seconds. So 1 minute is 60 seconds, and square that, because again there's 2 factors of minutes. So 94 times, what's 94 squared times 2 squared times pi squared divided by 60 squared, and then divided by negative 0.242 gives us a displacement of 400 revolutions. So it would take 400 revolutions for this to come to a stop. Oh, wait, nope. We lost a factor of 2 here. So the minus 2 there, we lost that minus 2. That turns into the plus sign, but we're off by a factor of 2 here. So again, 94 times 2 times pi divided by 60. Square that whole mess. Divide by 0.242 and divide by 2. So 200 revolutions. Before we come to a stop. All right, a couple other things we can mention here. We've talked about being able to calculate relatively simple shapes. We can also build up more complicated shapes by basically gluing simple shapes together. So for instance, you could have multiple disks, each of which you can have a 1/2 mr squared moment of inertia associated with them. And to calculate the composite moment of inertia, you just add them together. Since the moment of inertia is proportional to mass at distance, if the mass of your object is concentrated towards the axis, it will be easier to rotate than if the mass of your object is way out on the edge. It will have more rotational inertia for the same amount of mass if your mass is concentrated around the outside as opposed to concentrated in the middle. Let's do another example. It says a pulley consists of a large disk of radius r and a small disk of radius little r that are welded together and mounted on a horizontal frictionless axle through their common centers. The moment of inertia of this pulley is I. So we're just going to do this symbolically. A box containing a turkey of mass capital M, this one over here, is suspended from a rope wound around a large disc, and a box containing a pumpkin of mass little m, this must have been a Thanksgiving themed problem, is suspended from a rope wound around the small disc. The ropes don't slip on the disc, so we have a rolling or a turning without slipping condition here. Which is actually not even all that complicated. If we look at this, then on that inner wheel, in that inner part of the pulley, we have a force being applied here at a distance little r, and the magnitude of this force is our little mg. It's just the weight of our pumpkin. And then we have a bigger circle here with a radius capital R, and a force here, capital mg. And so the torque applied at both of these, this one will produce a torque R crossed into F upward, a twisting torque like that. So this will produce a positive torque. Torque here is plus our radius r times our force magnitude mg, capital Mg. And over here, this is our radius vector pointing in that direction, curled into our force vector pointing in that direction. That'll be a downward or twisted torque this way, a clockwise twisting torque. So a negative torque over here is going to be minus little r times little mg. And so the total torque, torque A and torque B here, I guess, will be the sum of torque A and torque B, which would be big R, big M times G, minus little r, little m times G, or in other words, G times big Rm minus little r, little m. And the acceleration then is just going to be torque divided by inertia. So that's going to be our G times big R, big M minus little r, little m divided by our inertia I. And if we had values for these masses and radiuses and this moment of inertia, we could calculate a value or a magnitude for that acceleration, but we've calculated at least in terms of an expression, an equation here. All right, one last concept to cover here, which is that sometimes it's easy to calculate, for instance, the moment of inertia around some nice symmetry point. So for a circle or a sphere, for instance, it's very easy to calculate the moment of inertia from the center of that circle, and much harder to calculate the moment of inertia around this point over here. But remember, it matters where the axis is. So if there was a way of going from, well, I can calculate the moment of inertia easily around, for instance, this center point, but I want to know what's the total rotation of inertia if we were rotating around a point on its edge, then we would need to use a relationship, which we're not going to prove here, but we're going to use, which relates the moment of inertia around the center of mass to the moment of inertia of an object around any point at distance from that center of mass. And basically, you say the moment of inertia at some point distance h here from the center of mass. So if you know the the rotational inertia of the hammer around its center of mass, you can calculate the rotational inertia around a axis which is parallel to that center of mass, but separated from it at a distance h. And basically you say, well, it's the rotational inertia around the center of mass plus this term here, which assumes essentially that all of the mass is at that center of mass, and so we have a point mass at a distance h squared, And so if you know the center of mass of your hammer, the center of mass inertia of your hammer, you just multiply it by the mass of the hammer times this distance squared to get the rotational inertia down here. What this means is that, for instance, the center of mass rotational inertia of a pen is smaller than the rotational inertia of that same pen wiggled around its end, and you can feel that if you wiggle a pen or a pencil around its center. It's a different feeling than if you wiggle a pen or a pencil around its end. It takes more pressure from your fingers to wiggle the pen around the end than it does to wiggle the pen around its midpoint. So let's do a little bit more complicated moment of inertia problem here. So it says, let's model Thor's mighty hammer Mjolnir as a rod of length L and mass M handle attached to a rectangular prism, a box, of mass M head, width W, and depth and height both D. All right. Write an expression for the total moment of inertia for Mjolnir rotating around the end of the handle where the strap attaches. The moment of inertia for a rectangular prism around its center of mass is md squared plus w squared over 12. All right. So this object, this composite object, is made up of a rod of length L. And at the end of that rod is a box-shaped object, height and distance D and width W. Okay, so we're going to rotate around. Here's our axis point. And what we can do is we can go back and look up, for instance, the a rod around its center, that's 1/12 ml squared, but a rod around its end is 1/3 ml squared. So the moment of inertia of just the handle, that's easy enough to calculate. It's just 1/3, 1/3, 1/3 times the mass of the handle times its length, L squared. Okay, we just got that straight off the table. Okay, the moment of inertia of the head here around its center of mass, so that would be the rotational inertia of just the head part here rotating around its center of mass like we see here. That's the mass of the head times d squared plus w squared over 12. But our head isn't rotating around its center of mass, it's rotating around a point distant from the center of mass by L plus d over 2. So the actual moment of inertia of our head here is this m head d squared plus w squared over 12 plus mh squared. So plus the mass of the head, and the distance here is L plus d over 2 squared. Okay, so we can expand that out a little bit if we wanted to, but in this case, it may be simplest just to let that sit because this is going to expand into something ugly. Yeah, we could mix this d with that d a little bit, but it's actually probably simpler just to keep those two terms separate when we go ahead and evaluate things down here. So the total moment of inertia of Mjolnir here is going to be the handle plus the head. So that's 1/3 the mass of the handle, L squared, plus the mass of the head times d squared plus w squared over 12. That's the head around its center of mass, plus the mass of the head at a distance of L plus d over 2 squared. So we've got 3 terms here for our moment of inertia. And if we've got a mass here of 100 kilograms for the head part and a handle of 5 kilograms, so the mass of the handle is 5 kilograms. The mass of the head is 100 kilograms, and D is 0.1 meters, W is 0.2 meters, and L is 0.3 meters. Then we can go ahead and calculate here. Everybody's testing. All right, we can go ahead and calculate that's 1/3 times 5 kilograms times 0.3 meters squared. That's the first term. Plus 100 kilograms times 0.2 meters squared plus 0.1 meter squared all over 12. And then our third term here, 100 kilograms times 0.3 meters plus 0.05 meters squared. So we'll take this a term at a time. 0.3 squared times 5 divided by 3. This first term is 0.15 kilogram meters squared. The second term, 0.1 squared plus 0.2 squared divided by 12 times 100 is 0.417 kilogram meters squared. I guess we'll call that 0.42 just to keep this the same significant figures. And in our third term, 0.3 plus 0.05 squared times 100 is 12.25 or 12.3 kilogram meters squared. So 0.15 plus 0.42 plus 12.3 gives us a total moment of inertia here of 12.87 kilogram meters squared. That's a little bit more complicated than you're probably going to run into on an exam. But certainly something, if you take your time and do it piece at a time, it's not too difficult. All right. Next time we will look at energy in the context of rotation and also momentum in the context of rotation. So conservation, energy conservation, momentum conservation, work, things like that in the context of rotation. All right, till next time.